And basically, the whole idea is the human brain consists of multiple neurons and like chemical and electrical impulses basically get transmitted from one neuron to another neuron based on different things. Like, let's say if we are observing a photo in front of us, our eye will observe that some signals will get transmitted right from the eye till our brain, and then we understand that, okay, we are looking at a dog. So that is where neurons are the building blocks in the human brain, which helps in transmitting as well as comprehending the information. And the inspiration of neural networks is to build artificial neurons which can kind of simulate those kind of signals. And that is where you have aspects like weights and biases and nonlinear activation functions, which basically kind of try to simulate what the brain does in terms of passing in those impulses from one neuron to another neuron. And the training of neural networks is such that you usually start with some label data in most cases, like let's say the photos of the dog or the mop. You will forward those images through a multi-layered neural network. The network will make some predictions. Obviously, initially, the predictions will be not correct. A lot of them might be wrong. That is where you end up computing the error based on the true labels from your training data, and then you update these weights of the neurons. And this process continues again and again till your model reaches a certain level of accuracy and the error gets reduced. And that is known as the process of backpropagation. So those of you who are interested in the conceptual details, definitely I recommend diving into it once you get deeper into neural networks. And the good part about neural networks is that in case of traditional machine learning, like I said, you would have to automatically, not automatically, but manually extract features from images. Like, okay, where could the nose be located, the eyes be located, the edges of the images, the corners, the patterns, and so on, using traditional aspects like image processing. And once you extract the features, then only you can build a model, like let's say use a logistic regression model or something. But in case of deep learning, the great part is it will automatically help you extract features without you having to sit and manually extract the features. And that is where models like artificial neural networks or convolution neural networks can help in kind of doing these tasks. And in terms of the word deep in deep learning, usually if you have like more than 3 or 4 hidden layers which have multiple neurons, that is typically known as a deep learning model. And again, that is just a terminology. The main thing for you to remember is whenever you have a multi-layered neural network architecture where each of these with multiple neurons is known as a hidden layer, it is called a deep learning model. And why is deep learning being mentioned so much in today's world, and why has it become more important? So the next few slides will kind of try to answer that question. One of the main things is if you are considering a career in data science in the industry in the future, if you look at this slide, this kind of shows you that the adoption of deep learning is massive, and almost every domain or every industry in some way or the other is trying to leverage deep learning to solve really complex and challenging problems, but real world problems. Like in case of consumer products, you can see like chatbots, personal assistants, providing you personalized recommendations, and then AR, VR, robots, a lot of things. So deep learning is being used in each and every one of these applications. Same in healthcare in terms of finding out new drugs, medical imaging-based diagnostics, providing patient care recommendations, and so on. In case of finance, as you know, in terms of building trading systems, finding out if fraud transactions are occurring, personal finance, automated risk mitigation. So basically, these are all real-world problems where deep learning is being used. In retail and e-commerce, I mean, it's pretty popular in terms of deep learning, where you can have recommendation systems, sales and marketing lines, optimizing the supply chain, inventory management, and so on. Even the government has started leveraging deep learning in a lot of aspects like smart cities, increasing safety, detecting in case there could be some terrorism activities based on live video feeds. And you can see, like, I'll not go into too much in-depth discussion in these other domains, but the whole that in every domain, no matter how different it is from the other domains, there are use cases where there is definitely a scope of deep learning, and companies have actually started using deep learning to solve these problems. Now, in terms of how is deep learning effective, just as a refresher, when you are solving problems using traditional machine learning problems, that is where you end up having to do a lot of manual feature engineering to extract different features from the data, which you can feed into a model, which costs a lot of time. But in case of deep learning, in most cases, you can let the model itself automatically figure out the right features to solve the problem. And this shows you an example in case of a facial recognition system where a convolution neural network is the architecture being used. And what you need to know for now is that there are multiple hidden layers, as we discussed in a neural network. And each of these hidden layers focus on extracting automatically specific features, which can be useful for doing the facial recognition task, like finding out the edges, the corners, nose, eyes. So it'll automatically try to find these patterns, and you don't have to sit and manually code these rules or code these feature engineering techniques. And that is where you can iterate very fast. You can build deep learning models faster, and you can solve the problem and basically try to improve on your baseline models faster with deep learning. And that is the reason why it has become more and more effective in solving problems like facial recognition, detecting cancer, and so on from medical images or from visual images. Similarly, in case of audio, as you know, like if you talk to a personal assistant like Siri or Google Assistant, it will basically take in your audio data and it will basically try to answer your question. And that is where also you have models being used like convolution and recurrent neural networks, where it will translate your audio signals to text. So that is known as a speech to text system. And then that text could be translated into something else, like another language if you're doing language translation, or it will do something like a Google search or an information retrieval query to get you the answer for your audio query. And another reason for why deep learning models have become very effective is that scale enables deep learning models to perform better. Larger your neural network and more the data you have, usually you end up having a really good performance in case of most problems. Bigger and more complex architectures are also being released almost every other month from a research perspective. And you're also having newer models, which is leveraging concepts like transfer learning, which we will talk about soon, where even if you have less data, it will perform better. And like I said, whenever you have very complex problems like understanding video data or translating one language to another language or speech to text, image classification, and so on, it's very difficult to do it with machine learning because machine learning models can't scale to multidimensional data. And that is where I think deep learning has become really effective to handle these problems at such a large scale. So in short, just to summarize, these are the main areas of what has driven deep learning to be so effective. Nowadays, you have more data. As you know, you might be hearing big data everywhere. So you have a lot more data now. You have new models and new research being released almost every other week or every other month in terms of better and faster, as well as more complex deep learning models. You have a lot of open source software, like knowing some aspects which could be reused to learning a new instrument. In the same way, if you know underlying fundamental concepts of math and statistics, it will be easier for you to pick up machine learning. So in case of the machine learning or deep learning field, transfer learning kind of means the same thing. For traditional machine learning problems, what happens is you usually start with a single data set, like let's say fraud detection. You will build different models, find out the best model, and you will have a learning system which can help you in predicting fraud transactions. Now, let's say if you get another new data set with a new problem, let's say predicting hardware failures, you will again start from scratch and then basically build a model and a learning system. In case of transfer learning, the whole idea is if we are solving the problem of fraud detection for classification, or if you're solving a problem like image classification, and we have a large data set, can we basically build a model which will extract and learn different weights? And can we leverage and reuse those learned models' weights and reuse them to solve a new problem instead of again training a model from scratch to solve basically a new problem in a new domain? So one example could be, let's say, if you have lots of images of human faces or lots of images related to different categories of animals and humans, different non-living objects, and so on. And if you build a model to learn how to classify those images, you will end up with layers of that model, which will be very effective in extracting features from the images. So let's say now if you have a data set to whether you want to detect cancer in a scan, a medical imaging scan, you could reuse that model from before and then try to repurpose it to solve the problem instead of training a model from scratch. Because often in healthcare, you will not have a lot of data. You will have less data usually. So that is where instead of training a model from scratch, which may not give you good performance, why not use a model which already knows how to extract features well from images and then just try to tune that model, that is known as fine tuning, to basically solve this problem of cancer detection in a much better and effective way. And that is where a lot of organizations and companies have built these pre-trained models, as you can see over time. Because training deep learning models from scratch can take a lot of time. And also often you don't have enough data to train a deep learning model, which will give you a good performance. So that is where you can leverage all these pre-trained models, which have been built by universities and companies on large scale image data in this case. And then you can just pick up this model and start fine tuning it for your own problem. And nowadays you have models for solving problems in image, audio, and video domain, as well as in the text domain, that's natural language processing. So these are like models from natural language processing, where you can pick up a pre-trained model and start using it, let's say, to predict the sentiment of movie reviews, or start using it to build a chatbot. So you have these models which have been trained on a lot of data, and you can start fine-tuning and applying it to your own problems. And that is basically the advantage of transfer learning, where you can use pre-trained models and tune them to give a better performance than trying to train a model from scratch on less data. In terms of deep learning frameworks, if you're interested to try out these techniques, these are a wide variety of deep learning libraries which are out there. This is slightly dated from 2017, but most of them are still active. But if you want to explore and build your own models, I would recommend to try out either TensorFlow, because now Keras is a part of TensorFlow too, or you can try out PyTorch. Both are pretty popular, and you can basically build your own deep learning models using Python. In terms of deep learning model architectures, we won't go into too much details given the scope of the session, but just so you get a feel for what kind of models are out there. So you have convolution neural networks, which can be used to do image classification, object detection. You can even use it for problems like speech to text and so on. And then you have models which are basically focused on time-based data, like recurrent neural networks, long short-term memory networks, gated recurrent units, bidirectional. So you can use these models to basically work on any kind of sequence data, like let's say looking at stock price data to predict the price of the stock tomorrow. You can use these models. Taking in a sequence of words to predict the next sequence. So that is where you can use it for things like predicting the next word based on previous words. And that can be useful for chatbot-based systems. And then you have autoencoders, which can basically be used to do tasks like denoising, where if you have an image with a lot of noise, you can pass it through an autoencoder and remove the noise. And then problems like encoder-decoder models can help in solving the problems like language translation, where it takes in a sequence of words in, let's say, English language, and then it translates it into another language from the decoder side. So that is where you can use encoder-decoder models to do things like language translation. And as I said, transformer models give you a bunch of encoder-decoder layers in the model, and you can use these models, which have been trained on a lot of data, to solve different problems in NLP, like text classification, sentiment analysis, question answering, summarization, and so on. So let's talk about the use cases now, which will be more interesting. So the first case study is about trying to predict data center device failures. So as you know, in any company, usually they will have a lot of network devices as well as data centers. Like now you're logging into Teams. So Teams basically is an infrastructure being run by Microsoft on their data centers. If their data center goes down, then Teams itself can go down. So that is where you need to ensure that you can have some kind of systems in place which can predict beforehand in case a data center can fail or it might be going down. So that is where the thing is, can we leverage historical data around device failures to predict when can a device fail in the future? And can we predict it with a good lead time? Because if you predict that the device will fail after it has failed, then it is not very useful. And that is where we leverage historical data from around 2 years worth of data, as you can see. And you have events data, like you have different events happening in the data center, like which systems are connecting, what is the CPU utilization, disk utilization, network speed, various things are happening in terms of events. And then we try to build windows from our historical data that for this window of data in time, after this, a failure had occurred, let's say in historical data. So basically, we try to build windows of data in terms of when the device was functioning normally over time. That is known as a good window. And when there was a nearby failure after some events had occurred, that is known as a bad observation window. The reason for doing this is we want to ultimately predict or classify that if we take in a new window of data for events, let's say, which is happening in the data center for, let's say, the last 6 hours, can we feed this to our model and can it predict automatically that whether a failure might occur or not? So that is where we need to build our training data also in the same way so that our model can learn from historical failures. So how did we go about translating this time-based data into a deep learning problem? What we did is we converted this events data into a multivariate time series data. So as I said, there are various events occurring. Like let's say event E1 is the disk utilization, E2 is maybe a connection request happened, E3 is maybe a connection failed, E4 is maybe a new system is connecting. So you get the idea. These are different events. And on the x-axis, you have time. So let's say for the first 5 minutes, how many connections happened? What was the CPU utilization? So in this way, over a period of, let's say, 6 hours time window, you can build a 2-dimensional heat map of events occurring over time. And that is what we do here. It is known as a tensor in deep learning terminology. We basically have a 2-dimensional matrix of events occurring over time. And this window of data basically behaves like a heat map of all the events occurring in that time interval, like let's say 6 hours. And the interval in this case, as you can see, we have divided it into 5 minutes. So every window subset in the x-axis is 5 minutes. And one is basically like, let's say one event count occurred for E1, and then for E2, nothing had occurred, and so on. So in this way, we try to get the counts of different events over time by slicing the time interval into discrete uniform sub-intervals of, let's say, 5 minutes each across the whole 6-hour window. So once you have your events data in the form of a heat map, this basically looks like an image. So then what happens is you can use this image data and you can pass it to a model which is specialized to extract features from images very efficiently, and that is known as a convolution neural network. So that is where we use the convolution neural network to automatically extract features and try to predict whether a failure will occur or not. And this kind of shows you that initially we started with building a manual convolution neural network where we tried to train a model from scratch. But then we basically went into transfer learning where we took a pre-trained model, which let's say Microsoft has trained on a lot of image-based data. And we passed in our data and tried to train it on the label data to predict whether a failure will occur or the device is good and no failures will occur in the future. And based on that, as you can see, like we tried out different models, and the CNN model basically gave the best performing model, which could predict a lot of the failures, as well as the false positive rate was around 10%. So that basically tells us that with deep transfer learning, we didn't have to do much of feature engineering. We could use a pre-trained model and get a good performance. And building this model took much less time than all of these because we had to figure out different features manually and train different machine learning models to get the best performance. The next problem is interesting. It is around malaria detection, which is a healthcare based problem. So, the whole point of why we need this is, as you know, malaria is prevalent across the globe, especially in tropical regions, as you can see in the if you consider this belt, right? Because in this area, basically, you usually have more heat coming in. And that is where, if there is a tropical weather environment in terms of there being more heat or more temperature as well as more humidity, that is where mosquitoes tend to thrive. And if an infected mosquito bites you, there could be the possibility that parasites will get into your blood and start destroying these red blood cells, as you know. And that is not a good sign because that basically leads to you having the malaria disease. And in case you are not treated for malaria, it can lead to a lot of complications. So that is why it's recommended that if you are prone to getting malaria, it is detected as soon as possible. Now, let us understand the challenge with malaria detection. So, if you look at the image on the left hand side, it kind of shows you the process to detect malaria, where you end up having a sample of blood taken, it is smeared on the slide, and then the image, the microscopic magnification image is extracted from the slide. And then there is an expert who will sit and count the red blood cells and look at the overall visual structure of that image scan from your slide, and then they will try to say whether the person has malaria or not. And this is a problem, especially in rural areas or areas with lack of access to good healthcare, because there may not be that many, let's say, experienced professionals who can do this at scale. There will usually be, let's say, one person who comes in every 2-3 days or maybe once a week. And if they are not there, then that is very costly in terms of people, let's say, who already have malaria. They can basically have problems because by the time they come in after a week, maybe they have the illness already being in a serious condition. So that is where the whole idea is, if you already have labeled images of people having malaria and not having malaria, like healthy cells and infected cells, can you train a deep learning model? So all people would have to do is just take that slide with the blood, get the image, and then pass it to the model, and the model can see whether the person is prone to malaria or not. And these are basically how the blood smear slide images look like. And again, this is already labeled data from before. So this is where you can see that some of these are basically blood smear slide images with malaria. And as you can see, some of these are healthy. So the whole point is, if you have a decent amount of training data with cells with malaria and healthy, can you train a deep learning model which can automatically start predicting whether the person has malaria or not? And that is what we do here. This is the process which was followed. You get a labeled data set of cell images. We had around 17,000 training images, and we validated and tuned the model to improve the performance on 2,000 images. And then we had 8,000 new images as the test data to check the performance of the model. And this is where we tried out different approaches. Like, one was training the CNN from scratch, which is like something like this, where we are playing around with the layers. We are not using a pre-trained model. The other option is using a pre-trained model, like, let's say, a VGG16 or a ResNet, which companies like Microsoft, Google, and so on have built. So that is where the other option is to train a pre-trained model. And the other last option is you take a pre-trained model and you open up its layers so that you can fine-tune the weights based on the errors which your own data set is generated. And this is usually recommended because the pre-trained model might have been trained on, let's say, images of cats, dogs, and other things. So it is recommended to tune the layers and tune the weight so that the knowledge can be adapted to solving your own problem, which will be slightly different. And then the idea was to compare these model performances. And as I said, in transfer learning, the idea is you take a pre-trained model which was trained on a large data set. Like ImageNet, if you Google ImageNet, you will see that it has millions of images with around 1,000 different classes or categories. And we can solve the problem of malaria detection by applying and transferring the knowledge of this pre-trained model in the context of our problem. So that is basically the focus of transfer learning. And this is one of the models which we used. This is a pre-trained model known as VGG19 because it has 19 convolution pooling layers overall for feature extraction. So the main thing to remember here is that VGG here stands for the Visual Geometry Group, and that is in the University of Oxford. So Oxford University researchers had actually built this model and trained it on a large data set of millions of images. Now the idea is, can we take in this model and can we adapt it to our own data set? But we don't want to predict the 1,000 classes of, let's say, cats, dogs, cars, and other types of classes, right? We want to predict only whether the person has malaria or not. So the last few layers we will remove, and then we will add in our own layers of trying to predict whether the output is going to be the person has malaria or not. So that's why the last few dense layers we will remove and we add in our own layers. But these layers are extensively focusing on extracting features automatically from the images. And that is going to be useful because we definitely need that to be able to extract the right kind of features from these images, right? Whether the person has malaria or not. And this is basically one of the learning curves which shows you the model performance in terms of the accuracy over different training cycles. And you can see that we reach close to 96 to 97% accuracy, which is pretty decent. And this shows you the power of transfer learning. So if you train with a CNN from scratch on only this data, you get around 95% as the performance. But if you fine tune a pre-trained model, you actually end up getting slightly more. And after 90%, every 1% accuracy also means a lot in terms of having a good model, which can basically predict with a lot of precision and less false positives whether the person has malaria or not. And I think this becomes very useful, especially in healthcare-based problems, because you need models with a high level of precision. So this kind of basically showed the fact that pre-trained models can work on data whenever you may not have millions of images, and you can still get a good performance. The next use case is in a completely different domain, which is in the area of cybersecurity. So as you know, a lot of you might be writing your own code in terms of either coding in C or C++ or Java or Python and so on. And whenever you're building any system, you don't code everything from scratch. You might be using some libraries. Like if you're loading a CSV or a JSON file, you will use usually a library to load in that file. Maybe if you are doing some kind of a operation like web scraping, you will usually use a library to do that for you in your code, because you will be focusing more on solving the problem. So that is where developers don't code everything from scratch. They do depend on code written by others, thanks to open source software, as you know, open source libraries and so on. And that is where we need to understand what are dependencies. So dependencies are basically open source libraries which we can use to solve our problem. Like we discussed about TensorFlow, PyTorch. Those are also open source dependencies which are dedicated to solving deep learning problems like building models and so on. So these kind of show you different open source dependencies. Just some examples, like these are libraries to work with Google Cloud. These are libraries to work with deep learning models and so on. Now, the challenge with these open source dependencies is, as you can see, for different languages, like for JavaScript, for Java, for Python, and so on, the number of dependencies have been increasing over time in a nonlinear fashion, which means more and more libraries are being released over time. Now, the challenge is with these libraries being released, there could be security issues in these libraries. And that is where you need to understand what are security vulnerabilities. So basically, any kind of bugs in the software which can lead to someone taking control of your system or attacking your system, that is known as a security vulnerability. And that is where vulnerability can be a mistake in the software code, because if someone is building the library, it is not like they will intentionally make that error, because it could be unintentional in most cases. But that is where you have malicious attackers who are sitting day in and day out just to figure out if there is some issue or some bug in the code which they can exploit and mess up your system. And that is where you need to stop those security vulnerabilities. But the problem is, because so many dependencies and open source libraries are being released like every year, the developers are more focused on pushing out features, right? Rather than just day in and day out sitting and focusing on whether there are security issues in their library, because they have to push out features also. Otherwise, they will not get paid, or let's say they will not get the recognition or the adoption of their library in the open source community. And that is where what has been observed is there is an increasing trend of vulnerabilities across the different libraries, across different language ecosystems, as you can see. And often vulnerabilities are present, but they are not disclosed as CVEs. So CVE is basically known as common vulnerability and exposure. And there is a database in the US called the National Vulnerability Database. In case an issue is found in any library, it has to be publicly disclosed to everyone. So often what happens is they are present but never disclosed. The time to find out a vulnerability and then disclose it can take a lot of time. And if there is an issue present, probably hackers already know about it and they are already exploiting it. So that is where the idea is, can these issues be resolved using some kind of an automated system? And that was one of the key objectives in this problem, where we tried to proactively predict these vulnerabilities across direct and transitive dependencies in this Golang Kubernetes ecosystem. So that is where, just to brief you on this, Golang or Kubernetes. So Kubernetes is basically a framework which can be used to scale applications automatically. You don't need to dive too much into details, but just so you know that Kubernetes is an ecosystem which can be used to scale applications automatically instead of you buying thousands of servers and then figuring out how much demand you need. And Golang is a language just like Java or Python, which is used as the programming language to build this Kubernetes ecosystem. So what we try to figure out is, a lot of people will be discussing about issues in the source code of Kubernetes, like developers from, so Kubernetes, by the way, is developed by Google. So developers from Google itself, as well as companies who are using Kubernetes, they will be actively discussing about this in open source forums, on GitHub issues, pull requests, and so on. So that is where what we did was we built this complex system where we pulled in open source data from GitHub events, pulled in forum discussions, pulled in open source bug reports, and then we extracted the text data from that, and we passed it through some pre-trained deep learning models, which include using natural language processing based models like transformers or embedding based models, which could basically help in predicting whether there is a possible security issue or not. And as you can see, this monitors over 850 libraries at scale. So this is a pretty complex system which has been built into an end-to-end product. And this is where models like transformers have become very effective, where a transformer model is basically a stacked encoder-decoder model, which is used on, basically, which is trained on a lot of data. So by default, Google trains this model, like BERT is known as bidirectional encoder representation from transformers. So BERT is a transformer model, which is actually trained on a lot of data. Like it is basically trained on all the data available in Google in the form of the whole Wikipedia database itself, Google crawled web pages, and so on. So the idea is it already has some contextual information about security. And now we are just fine-tuning it on our own data and then basically trying to predict whether we have a security issue or not. And that is where fine-tuning a pre-trained model is much better, because in our case, let's say we have 100,000 issues as they are not serious security vulnerabilities, and we have, let's say, only 600 issues as they are serious security vulnerabilities. So it's a highly imbalanced data set, and that is where using a pre-trained model and fine-tuning it gives a much better performance than training a model from scratch. So I'll not go into too much details of this, given that this is very technical, but I just want to focus on this. So like I said, the data set has over 200,000 events which are not security related, and only 650 which are related. So you can imagine that this is highly imbalanced data. And based on the model, like I said, the BERT model, which is a pre-trained model trained on almost all the data available on the internet, when we fine-tuned it, you could see that we were able to accurately identify 80% of the probable vulnerabilities, and the precision was around 71%, which gets pretty challenging because you have only 650 issues out of 200,000. So that is where, again, transfer learning kind of showed the fact that if you leverage a pre-trained model and tune it, you can solve this kind of a problem with a high level of accuracy than, let's say, getting something around 50%, which was what we were previously getting when we were trying to train a simple artificial neural network model from scratch. The next two use cases are in the imaging domain, so basically in image processing and so on. So that is where the first one I want to talk about is image super resolution. And in image super resolution, the idea is this is used in a lot of applications, like let's say when you want to restore an image of poor quality, but you don't have like any good quality images, right? Because you only have a poor quality image which you want to restore. So that is where the focus is, that we have a low resolution image which is degraded, and we want to use a deep learning model to build a visually pleasing high resolution image. So let's say, just to show you an example, this is, let's say, an image in low resolution. As you can see, the image is pretty small. So if you were to resize it, it would appear very pixelated. But using deep learning models, you can see that this is the generated image, which is around 4 times larger than the original scale of the image, but it still looks pretty good from a visual quality perspective. And it is used in various computer vision tasks like security and surveillance, medical imaging, image generation, and so on. And some of the architectures which are being used here, which are, again, enhancements leveraging convolution neural networks, are things like residual dense network, residual dense network, generative adversarial networks, and so on. Now, I won't talk in too much detail about the technical aspects of these models, given that it is pretty complex, but I will talk more from a use case perspective. So the whole point of us trying to build such a system was that we need to train the model to understand that, okay, if this is a low resolution image, what does its high resolution counterpart looks like? So that is where we had label data around probably 2,000 to 3,000 images, where we had the low resolution image, like let's say we had this image, and we had the corresponding high resolution image. So we want to feed both of them, like let's say this is my X and this is my Y. We want to feed both of these to the model, and we want to make it learn from different patterns extracted from the images to automatically figure out that, okay, if this kind of an image is being passed in, how can I expand it to 4 times its resolution? And that is where the model architecture uses a superscaling network based on residual dense network. And it uses a generative adversarial network for training. And it uses aspects like VGG19 to extract different features from the image to figure out what is my loss. Because ultimately, like I said, in any neural network model, you want to reduce the loss of the model so that you can make better predictions. In this case, generate better images. So this is like how the model architecture looks like. As you can see, there are multiple convolution layers, multiple residual dense block, and each of these blocks can be expanded into this architecture. So each of these red blocks is basically this architecture with multiple convolution and activation functions and so on. And basically, when you use multiple of these blocks, you end up with something like this. This is known as a residual dense network. So again, not going into the technical details, but basically what is happening is a bunch of feature extraction steps is happening here. And then it is trying to generate a high resolution image from the low resolution image. And how do we train the model to become better? So that is where we have the original high resolution image, right? Which is, let's say, the actual image in a good resolution in the training data. And we have the image which is generated by the model. So let's say this was the low resolution image. Our model generated this high resolution image. This is the prediction and this is the actual. So we do something like a mean square error based on features extracted to figure out how much the error is so that we can train the model using backpropagation and update the weights. So that is basically what is done here to improve the model to basically generate better quality images which are close to the true high resolution image. And that is exactly what is done to reduce the amount of noise present in the image and add in extra levels of visual details in the images. And then this is an example which shows you the image, which if at a lower resolution and you want to resize the image, it will end up being very pixelated. But if you use super resolution, you can blow up the image to 4 times or even 8 times its resolution, and still the visual aspects will be maintained in the image. So that is one use case where you use generative deep transfer learning. And the last one is being used in a lot of like photo editing applications. It's known as neural style transfer. So the whole point is if you have like an image of the Taj Mahal, as you can see here, and this is an image of a painting by Van Gogh, you can apply the style aspect of this on the content image as it is known here, and it will look like a nice painting of the Taj Mahal in this style. So that is where it is known as neural style transfer, which basically leverages, again, generative transfer learning to apply the style of the reference image. So basically, this image is my style image. I want to extract the style aspects of this image and apply it on the content image. So the content image shouldn't change the structure. The Taj Mahal should still be intact. The only thing which should change is the style of this image should be kind of similar to this. And that is known as style transfer. And it's called neural because you're using neural networks to do it. And as you can see, this is another example where you have an image of a comic book, like I think probably Batman, and you're trying to apply this dark kind of a style to, again, the Taj Mahal image, and you can see how different it looks. So overall, what happens is the objective of the neural network here is to retain the content of the original target image so that the Taj Mahal structure shouldn't get distorted. Like the pillars here shouldn't get removed or something. The structure should remain the same, but the style aspect of the style image should get superimposed on this. And that is where we again can use transfer learning to extract both the style and content-based features from both the images and then superimpose them. And that is what happens here. We do a lot of steps. I won't go into details about these because the focus again is to just give you an idea about the use cases. But what happens here is we extract the style representation from this image. We extract the content representation from this image. We do the superimposition. We compute the loss. We compute the gradient. And then we do backpropagation to continuously update the weights of the neural network to end up giving a model with the least loss. And again, we use a VGG19 model here to extract the features for us from both the style and the content images. And then this is how it looks like. So we pass in the two things. We extract relevant features, as you can see, at different layers of the image. And then we try to do the reconstruction by doing the superimposition. So this is how one of the features looks like for the Taj Mahal. As you can see, the overall structure of the image is maintained here in terms of the Taj Mahal content. We don't care about the style of the Taj Mahal, but more about the structural elements of the Taj Mahal. And then these are some of the style aspects of the painting, if you remember that Van Gogh painting, which we talked about. And then what happens is we try to find out in case there is any extra noise in this image. After doing the reconstruction, in case there is any extra noise in the image, we try to basically reduce the noise by using a concept called total variational loss, which tries to remove the edges, the extra edges in the constructed image. And then again, this is where we use optimization in the form of gradient descent. to basically try and reduce the loss of the image in terms of training. And then this is an example of how it looks like. So you have an original image, you have your style image, you do the superimposition, and you can see like by reducing the loss in terms of removing the extra edges, this is how it looks like as the final product. So overall, this should give you an idea in terms of the different applications of deep transfer learning. The idea here was, again, not to really dive too much into the technical details, given it's only a 1 hour session, but for you to get an idea that if you have pre-trained models, you can solve a wide variety of problems ranging from healthcare, infrastructure, cybersecurity, medical imaging, photo-based visual applications, computer vision, image processing, and so on. So that should give you a good idea in terms of the importance and the need of deep learning and deep transfer learning. These are some of my social links in case you want to reach out to me in the future. And yeah, that should bring an end to the presentation.
Thank you so much, sir, for delivering an amazing session. Now we have arrived at the question and answer round. The session is open for questions. You can unmute yourselves or type it in the chat box.
Hello. Actually, sir, I have a question. What do you prefer? Like, is it TensorFlow or PyTorch more? Because when you see, like, I am currently working with TensorFlow for a bit. I tried a project and I deployed it. So deployment was rather smooth, but when we see, like, when I searched in like Kaggle or others, I found that many of the people were encouraging more PyTorch than TensorFlow. Like when there is like in evaluation metrics, it performs better, something like that.
Don't know about evaluation metrics, but everyone will have their own opinion, honestly. I will say you should try out and pick the one which you like. And actually, at the end of the day, again, it depends.
But what about PyTorch? Like, is it really that good?
Nothing special. See, these are all libraries. Everyone will have their own opinion. So you should really try out and stick to something which you like using. Because see, at the end of the day, it is also based on what the company is using, right? So often if you're working somewhere, they may not even be using TensorFlow. You may have to then use PyTorch. So it's good to know the basics of both, but stick to one because you can easily learn the other and pick it up. But in terms of the capabilities, I think both are having similar capabilities. The other aspect is in terms of features. So I think deployment aspects in TensorFlow are still a bit superior because you have aspects like TensorFlow Lite and TensorFlow JS and so on, which are very easy to deploy on the edge. But PyTorch is also getting there. I will say in a couple of years, it will be also there. In terms of readability, I think PyTorch is slightly better than TensorFlow. But now with TensorFlow 2, the Keras API, you can do a lot of customization yourself. So from that perspective, I think you're still good with TensorFlow. But a lot of research which is coming out, like if you are into doing research or adapting papers from like research and trying to implement the models, you will see most of the code will be released in PyTorch. So from that perspective, I should say that it is good to know a bit of PyTorch in general, even if you are using TensorFlow. Yeah.
Okay, I got one more question for you. Like, can we really fix a good architecture for transfer learning? Like, just you showed that VGG19 with some fine tuning was performing much better as compared to any other ones. So, is it like that?
You mean like automatically figuring out, or?
No, means like for transfer learning we have various architectures, right? So one of them was
you have to try it basically. So VGG worked well in this case, but now you have a lot of much newer models. Like there is even transformer based models coming out for computer vision, and you have a lot of models around residual networks and even efficient nets and so on. So probably the thing is, if you benchmark on ImageNet data, they will say every model is better than the others, like based on the newer models. But on your data set, it may change. So the only way of knowing is really trying it out and seeing which is giving you a better performance by looking at the evaluation metrics.
Okay, thank you so much.
Yep.
Excuse me.
Mm-hmm.
Sir, I also wish to ask you a question. Since you are a Google developer expert, can you tell us about few popular examples in which Google has used deep learning algorithms?
Yeah, I think in almost every application they are using deep learning. Like if you're using Google Translate, let's say, then in the backend it will be using an encoder decoder based model, which is already pre-trained on a lot of data. So that is where it uses transfer learning. Google has worked with different villages. I forget which country, but they have deployed some applications which people can use from their phone, and that is where they have again used pre-trained models to detect plant diseases. So that is where also they have used transfer learning. And other applications, again, even the Google search engine, when you're searching something in the backend, there is a pre-trained model which is actually running. Google speech to text service, the Google Assistant, let's say on your phone. All of these places is where elements of transfer learning are definitely being used in general. Yeah.
All right, thank you.
Yep.
If anyone has questions, you can please ask to Sir.
You can drop your question in the chat box, or you can even unmute yourself and ask.
Okay, I think I see a message in the chat. Normalization depends on the type of data you're using. If you're using numeric data, it can be like scaling your data using something like standard scaling or Z scaling. If you are, let's say, having image data, you need to scale the image pixels from 0 to 255 to between 0 to 1, because that can help the neural networks train faster and converge better. So whenever you are transforming the data from one range of values to another range of values, that is known as the data normalization.
Oh, okay. We will move forward now. Um, Technology will never replace great teachers, but in the hands of great teachers, it's transformational. We feel extremely lucky that we have Professor Achama Thomas as a chapter advisor. I would like to request a chapter advisor, Professor Achama Thomas, to enlighten us.
Yeah, thank you, Gauri. So on behalf of GHRC, I would like to thank Dipanjan Sarkar sir. Sir has been already associated with us. In fact, he had been here for the first International AI Summit in our institution. And I remember that time also he had a very engaging session. So thank you very much for this wonderful session. It was really interesting and engaging. And I'm sure the participants would have understood the concept of transfer learning. It was introduced really well. And I like the choice of use cases also, as in you have chosen all different domains, the industry, healthcare, security, image reconstruction. So I'm sure that the use cases that you've discussed will definitely encourage our students to pick up more projects on deep transfer learning. So thank you once again. I hope everybody has enjoyed the session. Yeah.
Yeah, thanks a lot for having me. Yeah, I know I was there in the summit, and I know because of COVID and all that, things got difficult for
that was the
last
second one,
year.
sir.
Right,
last year it was difficult, but the first summit you were here.
Right. The first summit I remember. So yeah, I mean, good that we can still connect virtually and continue with the learning. And yeah, like you said, I hope the different use cases gives people inspiration to explore more. And yeah, hoping in the future we can meet again in person for more such events.
Yeah, sir. Thank you, sir. In fact, I do not know if you're aware, but we have started with this course on BTech in artificial intelligence and also BTech in data science. So we have started with these 2 degrees in our institution. And this is the second year. In fact, most of the students here are AI students.
Wonderful. That is really good to hear. I think these kind of initiatives will help more data scientists graduate who can really do a lot of things leveraging these technologies. Yeah.
Thank you so much, sir. Yeah.
Thank you so much.
Over to you, Gauri.
Thank you so much, ma'am.
Excuse me, sir. Could you please take your screen down?
I don't know if the camera will work because I'm using Teams.
I'm talking about this screen. I mean the presentation slides.
Oh yeah, of course. You mean the sharing, right? Hang on, give me a second. Yeah. Let me know if it's off.
Okay. Yeah. All right.
Now that we have come to the end of today's program, I would like to invite Ms. Rutuja Kargirwar, Secretary at IEEE CIS Student Branch Chapter, for vote of thanks.
Good evening, everyone. It's a privilege to have been asked to propose a vote of thanks on this occasion. I, Rutuja Kargirwar, Secretary at IEEE CIS, on behalf of the entire team, IEEE CIS Student Branch Chapter, GH Raisoni College of Engineering, extend a hearty vote of thanks. Our sincere gratitude goes to our guest of honor and speaker for today's event, Mr. Dipanjan Sarkar, for sparing his time and gracing us with his knowledge. The way in which Mr. Dipanjan explained different case studies in deep transfer learning was extraordinary. We are very fortunate to have you here, sir. Once again, thank you. I want to express my heartfelt gratitude to our Director of GH Raisoni College of Engineering, Dr. Sachin Antavle, sir, for his kind support. I would like to thank our praiseworthy delegates for adoring our event and sharing their opinions today. I also want to express my gratitude to our chapter advisor, Professor Achamma Thomas ma'am, for her guidance and support. No event goes smoothly without the coordination of audience. We all are overwhelmed with the cooperative and patient nature of our participants. Thank you once again. I cannot thank everyone enough for their involvement and their willingness to take on challenging tasks and stepping beyond their comfort zones. I would like to remind everyone to fill the feedback form or else you won't receive your certificates. Kindly do it now within 10 minutes and then you may leave the meeting. You may scan the QR code for the feedback form or you can also use the link shown on the screen.